Very good morning, all of you. I hope you have performed well in your second test. And after second test, I hope you have started implementing the backtracking. So just to recall and quickly have a recap that with the backtracking, I'm sure you have implemented various alternate algorithms. I have already discussed that using backtracking, you can implement n-queen, m-coloring, and the corresponding Hamiltonian cycle problems. Just to show you an idea of how those could have been implemented, I'll show quickly the solution for n queen and m color, which is similar to the corresponding implementation of n queen. So for m coloring problem, m will be supplied. So I have assumed m to be 4. I have shown the partial code last time. Here is a total code available. Effectively, this module is more or less same as n queen's main module, where xk being attempted for all m values, place being verified, and if place is acceptable, then the answer is printed and recursion is resumed. If I want all possible values to be printed, I will exit here to stop after one solution. Exit means come out of the program. Otherwise, recursion will automatically explore all possible values for each xk. That will mean automatically on every successful value also, program doesn't stop. Even if you write return, that will only have an exit or a break from the current recursive call, but doesn't stop the other recursive calls. Place function, effectively, I have to ensure that if the vertex is adjacent to the kth vertex which is being considered, and if both have the same color, then it is not acceptable. Otherwise, it is acceptable. So that can become a simple code. Similarly, for the Hamiltonian cycle, if you see this function remaining again exactly same the way we have done, n different values to be attempted. So I'm saying I'm trying to give the corresponding xk as 1 to n, means which vertex is to be traversed at this stage. If that vertex to be traversed is becoming a part of Hamiltonian path and subsequently cycle, it will be true, otherwise false. And how to check that? I say, fine, if there is no edge between current vertex and the last covered vertex, means the kth vertex, and the previous covered vertex, obviously return 0. Otherwise, I have to check whether the vertex is already covered. If the vertex is already covered, obviously it is not to be part of Hamiltonian cycle again. So return 0, false. If not, that means the current vertex is new and it is having a path from the previous adjacent vertex k minus 1. Then I will check if I have reached to not the last position, obviously return 1. If I have reached to last position and it leads to a cycle, it leads to a adjacency between current vertex, that is nth vertex, with first vertex covered, then obviously I will say return 1, else return 0. So this can become a simple code. Having said that, now I think I can resume with the next discussions. And so I'm sure this code will help you in better implementation. And I have also said that try the other implementation also as per the book also. Those who want to do better programming, they should aim to do the other implementation also as per book. Having said that, now I'll proceed to some new aspects. So programming paradigms, we have already discussed main philosophies, programming, or I'll say algorithmic paradigms. We have talked of 4 paradigms, divide and conquer. We have also talked of DP. We have talked of greedy. And we have talked of backtracking. But all of these, if you see, have primarily been dependent on using mainly 2 kinds of a storage. Storage for the data, we have primarily used either array or linked list. Both have its own advantage and disadvantage, but array has one of the best advantage that access of an element is in unit time. If you know the index, then it can be done in order of 1. The only thing is index should be known. So if index known, things are easy. And that's why array is most preferable. So in general, if I know the index, we have done. But what we did in graphs, actually the graph vertices, ideally in real life, the vertices will have some ID, maybe their name, maybe city name, maybe computer name, maybe computer MAC address, maybe computer's IP address. All these can become various graph vertices. Obviously, they are not going to be in the range of 0 to n minus 1. If not, then how your graph algos will work? So there is always a question mark. Although we have initially assumed that my graph vertices were numbered as 1 to n, we assumed that, and then things became easy. But in real life, it won't happen. So we need a solution that if I want to use array so that searching can be faster, how can we get the corresponding accessing or indexing done? Yes, dear friends, for that, the solution available is called as hashing. So hashing is a new concept which will be used primarily to generalize the arrays. And the generalization means that the indexing now will be much more easier. Why? In arrays, the index was the factor for searching. But what we need is certain key values to be used for searching. And for that, the hashing will be useful. So if I was directly using indexes, then it was array. In general, it means in case of a hashing, I will have a key value on basis of which the searching is done, and still I want the array to be used. How that will happen? Effectively means that key was the index in arrays. And that worked easily. But if the key was not indexed, then we have to really think of the possible solution. So if I want now the solution to be done where I'm going to work without that, I'm going to talk of that. So till now, I say that one way was that key itself is index. That was a starting point. And this concept, if I use in hashing, then it is called as direct addressing technique. We have already used that. We are familiar with this. For example, if I say my keys are always, say I have my keys always in the range of 0 to m minus 1 or 1 to m, one and the same thing, where I mean m slots are available for the storage, then I can directly do the addressing. So hashing simply means that I have a storage table available, storage array available. In general, I will say it's a storage table or storage array, and it has got m slots. And I assume n values are to be stored. So what I require is that I have here all key values k1 to kn at somewhere in the universe of key values, and all k values are available. I want to ensure that for each key value, there is a some slot to which this maps. It could map anywhere. I'm not saying that they will be always ordered or like that, but effectively it means each key value, key I, should map to some address or to some slot on 1 to m, or in general, you could say 0 to m minus 1. One and the same thing, but 0 to m minus 1, because in arrays normally we use. So I say they should map to some slot. And this is what is purpose of hashing. So I should be able to do that. And that is what is to be done through this process. The advantage is obvious. So in case of a direct addressing, the key itself is equal to index. So that will mean my keys are 0 to m minus 1. Automatically, there is no confusion. always I am interested to do 3 operations. So I will say searching, insertion, and deletion for searching. So if I want to search means I am given my ST storage area or table or array and the key value which I want to search. So I will say if the key value is given, effectively within the ST at slot K is the direct value or the full record available. And I can effectively say return this full record which is stored here. So key based full records are there. Here I have key value, let's say that means K2 plus some other fields. Here I have Kn plus some other fields. So it's all full data available. So full record will be sent. And if it was not available, maybe I will have null returned or -1 returned if it was unsuccessful. But in both cases, I'm able to directly use the index without difficulty. And this works in order of 1 time. Insertion to be done, still easy. Insertion to be done, I am given again ST and the key to be inserted. I can directly put into ST corresponding place K and let's say full record is sent to me to be stored. So I will say ST K equal to full record. And obviously, if this was not present already, then it will be stored. If it was already present, I will say it's a duplicate or it is already present because this is there. Similarly, for the deletion from the ST, I want to delete the record corresponding to key K. So if I have to return the deleted value, maybe I will say I will have some temporary variable where I will store the corresponding element or full record. And then I will say ST of K to be equal to null or -1 so that for future I know that it is empty now. So for whatever empty notations I use, that I will store. And then I will say return the corresponding, let me just change this. This is creating some issue. So I'll just drag it here. Yeah. So I will say return and then temp to be returned. Now, this is also ideally order of 1. Insert is also order of 1. So I can see. So if the connection issue was there, I'm resuming. So I said that direct addressing has its own advantage and effectively I am able to do search, insert, delete all in order of 1. But obviously I wanted keys values to be properly available in that way. If not, let's say key values are strings. For example, city name, student name, or they are certain series, or they are fractional values, they are real values, vectors, anything like that. Then what to do? So I need a solution. So for those, obviously, I will say now those characteristics will decide how to do that. So for that, one thing can be that say if number of key values are very less, for example, n is very less, n is small, even if there are lots of strings, etc. For example, I say I have only 20 city names and through 20 city names, I want to store certain information, but because city names cannot become an index, so one solution can be maintain something known as a hash table. Loosely, it means it's a kind of an index page where I will have all 20 city names, let's say alphabetically arranged, say Ambala, let's say then I have Delhi, then I have KKR, let's say Mumbai, and so and so. And I say, okay, this will map to index, let's say 5, this will map to index 3, this will map to index 17, this will map to index 10. And then here I have a storage table where full record for, let's say at index 3, I will have record for the Delhi. So this is actually connected like this. This is connected like this. This is connected like this. This is somewhere connected like this. So just 1 second, please. Let me just save the previous recording and done. Fine. So now I will resume with the discussion. Yeah. So once this is done, then I can easily say this means this extra hash table is stored through which I can directly get the indexes. But obviously, searching for a key value in hash table will take time. Order of 20 if linear search was done. And it could be order of log n if a binary search was done. So, and if I see binary search, the data needs to be sorted always. Sorted will mean insertion will become more time consuming. So obviously, hash table is suitable only if I have small value of n. For bigger value of n, it will be obviously not suitable. And in that case, I need a better solution because I can't afford the searching time or sorting time or deletion time to be order of something. Ideally, I will prefer that my searching, insertion, deletion, all should be order of 1 if possible. That means my hash table is not a good solution if I have n to be big. Then what is the solution? If n is big or if n is reasonable, then we have other solution which we call as hash function. So that's a generic solution which can apply over a key. So if n is very big, then we need a solution. So the solution says that effectively I will apply some hash function over a key, and that will give me the corresponding index. And the index which I want is obviously has to be in the range of 0 to m minus 1. Because I have set n values, m slots, that's a standard word which we'll always use. So I want, for example, if I want to do something on corresponding city name, so if I am having, let's say, Ambala, if I have some hash function, I want hash function to be applied over Ambala, which tells me that it gives me value 3. So NH of any city name when I apply, it gives me some value in the range of 0 to m minus 1. Then I can definitely use this as a hashing function. So if I want to achieve that now, obviously I have to do some better programming, some better functionality, how to achieve that. Where I have to define hash function. But if I want to define hash function in a good way, primarily I have to ensure that my hash function is going to give the random or distribution to be good. It should not lead to same slots. And secondly, the time to calculate should be preferably order of 1. Because if hashing takes a lot of time, I can't afford that. So what I will say, if I am given hashing, whenever I'm given a key value k, which I want to search or insert or delete, I will apply h of key, and this becomes the index. And in hash table, at slot s of t, this is going to be the location for the storage or the search. So this calculation, if I am able to do in order of 1 time, probably I can achieve good performance. I want to do that. For that, obviously, my hash function has to be defined. So what my hash function do is my key values universe or my key values will be mapped. So it's a mapping of the function, or it's a function mapping this value to 0 to m minus 1. But now, obviously, in this case, there is a possibility of having collisions. I say I can have a value k1. I have another value k2. It is possible that h of k1 is equal to h of k2, but k1 is not equal to k2. Because whenever you are defining some mathematical function, and calculations could lead to that. If it happens like this, it is called collision, and K1, K2 are called synonyms. So you should know these terminology in any interview, etc. Also, this word can be used. So with hashing, or whenever you use hash function, obviously possibility of a collisions is there. Then you need collisions to be resolution or collisions to be resolved. So how will you resolve? Resolution, there are two techniques. One is known as chaining and other is known as open address. Now, chaining and open address. So if I want to say that, okay, this will be applied, then the process will be how to apply. So we will understand one by one both techniques. Chaining. Chaining means that if duplicacy is there, they will be stored in a chain. So synonyms will be chained together. And chain means effectively a kind of a linked list. Means anyone coming here, let's say some value comes here, some value comes. So over this place, some value K1 has been stored. Let's say, so that effectively means H of K1 meant this place and K1 is stored. Now you got another K2. You wanted to store. Let's say this also maps to the same address. That will mean I will insert K2 into this chain. And insertion will mean insertion at the starting will be easy because it will be faster. So I will insert at the start of the chain. So insertion for some value into storage table K will effectively mean insert full record of K into or at the front of the chain. At the front of chain, where is the chain? At ST H of K. H of K is a corresponding index, and at this slot, this is a corresponding slot, and at this slot, the corresponding record will be saved. So this will become the corresponding place where I'm going to record all this data. And this will be the insertion. So obviously, insertion can be order of 1 because at the front insertion makes things easier. I have to search ST for K. Now, best case, search is not going to be order of 1 always. Best case, say there was no synonym, only one data was there, or even if there was synonym available, it was at the start available, I could get it. But what about worst case? When will be the worst case? Yes, can you smell? Worst case will mean it can be as big as order of n. When? If all keys map to same address. That will mean the worst situation. What does that mean? Effectively means H of K1 is also equal to H of K2 and all are equal to H of Kn. All n keys map to the same address. That will mean obviously it's a poor hash function and I will never prefer to have such. But if I have a poor hash function, my performance is very poor, order of n searching time. Even deletion. Deletion also have to search correspondingly into the full chain. And if chain is of length n, obviously worst case, it will mean order of n. So order of n is never desirable. We should not go towards worst case. How to do that? How to ensure? That means my hash function must be properly chosen. How to choose that? Simple. Obviously, I should ensure the randomness of the distribution. If I can have perfect hashing, it means no collision happen and all hashing or all values lead to a different place. All slots are different. then obviously no collision. That situation is called perfect hashing. Like in direct addressing, or if there are unique values of keys which are in the range of 0 to n minus 1, perfect hashing is possible. Or other way could be that fine, I have students' roll numbers. Say students' roll numbers, for example, I say there are 1211 and 2001 onwards. If I assume that maximum, let's say 900 students are there in the college, in the total college, then I can say, obviously, my roll numbers could have been something like 12001 to 12900. Then even if I take these 3 digits through hashing, extract last 3 digits and use them as the corresponding addresses, then it can become a good perfect hashing. But it will not be obviously the situation with every data. So I have to think of finding perfect hashing possible. If perfect hashing is not possible, normally it will not be feasible. So perfect hashing rarely possible, especially we have a data in different ranges. Then we want to achieve uniform hashing. What does uniform hashing mean? Or I will say the better word is called it as a simple uniform hashing, SUH. So what SUH mean is that I am going to use a situation that any element, or when it is SUH, if any element which I am trying to store, or any element or corresponding a key is equally likely to be hashed or to hash into a slot which is any one of the possible slots, any of the M slots, irrespective of other storage, irrespective or independent of where any other elements or keys have been stored, have been hashed or stored. If it is so, then I will say this is called as simple uniform hashing. So it means the probability or possibility of any value is almost random and equal for every slot. Probability being equal for every key to every slot. So that will probably ensure that uniformity will be there and minimum collisions will be possible. Zero collisions might not be possible. So if I have uniformity, minimum collisions could be possible. And that can probably help in improving the situation. For example, I say in NIT KKR, you are well aware that roll numbers series for second year are 1211, 2001, and probably I have roll numbers up to 3200. Approximately, I have 1200 students. Similarly, for first year, my roll number series is in this range. So this is your second year. Similarly, first year, and similarly, third year and fourth year. So institute has approximately 1200 into 4, 4800 students. And according to that, I can probably think of making some hashing such that the corresponding digit of this tells the corresponding batch of admission. You are 21 admitted, 22 admitted, 20 admitted is third year, and 19 admitted is final year. And last four digits. So primarily these are probably playing a role. Can I combine this value and 1/2? So 21/22/20/19. This was your year of admission. And then you have 1 to 1200 as values. If you can think of making some hashing using these, probably you could map to a good simple uniform hashing. Still, in NIT Kurukshetra, the DASA students' roll number also could be, say, 12152001. So one student is 12112001, and one student has this roll number. So if I chose these digits based hashing, both will have same hash value. So same slot will come to these because these two combined are getting the hash function. So same slot will mean some collisions. But because I have chosen a good hash function, my collisions are going to be very less because few DASA students are there. So out of 1200, maybe I have only 13, 15 or 10 to 15 DASA students. Their roll number can have such duplicacy. So all that can be now managed, and accordingly, I say that my performance becomes critical to hash function. If I am able to choose a good hash function, I can make good choice. How to choose a good hash function? So when I want to choose a good hash function, the good hash function will actually require hash function to be planned in a way that correspondingly collisions are minimum. For that, primarily we are using good hashing through two different mechanisms. What are those two mechanisms? Let me just explain one by one. First good hashing function is called as a divisor method, which is quite common and quite useful method. For example, for NIT Kurukshetra, I said I have roll number, and roll number is my equivalent key. So I will say corresponding to key, this I will apply a mode function over M. M means I am having 1200 slots. So I will say K mode 1200 to be taken. The advantage being the addresses or indexes will come guaranteedly in this range, and I know that I need only 1200 students. Or if I have, let's say, for total college, this was only for second year. So total college has, let's say, 4800 students. So I will say K mode 4800. So K could be of any roll number of any year. But guaranteedly, my total students are 4800. So my correspondingly indexes generated will be these many. Total storage will get used. But obviously, I can see collisions will happen. They are possible because my hashing or my divisor is going to be like this. In general, when I say K mode N to be taken, M should be preferably prime number that helps in a big way. It is normally mentioned in many books also or many places that hashing performs well when prime numbers are chosen, because using prime numbers, the randomness of the corresponding mode operator will be there, and random distribution or simple uniform distribution could be possible. But obviously, choice of M is very critical now. If I choose M wrongly, even if slots are sufficient, my divisor might not work in every case. Hence, this is not a good method. So we will require a better method. That method I will talk next time. But if I know that chaining is there and I am going to get some collisions, how will be the performance? Performance using simple using chaining for collisions and simple uniform hashing assumed. So I'm not going towards worst case. Simple uniform hashing will mean that in general, the chain will not be very lengthy. For generic sense, let's assume n values are there, m slots are there. So n by m is called to be a load factor. And I assume this to be denoted as alpha. Now, if m is more than n, alpha is going to be obviously less than 1. I have more slots than number of values. So alpha less than 1. And this is ideal situation. Had there been perfect hashing, I will have effectively no collision. And because slots are sufficient, no collision will be guaranteed. If I have simple uniform hashing, minimum collisions will happen because slots are sufficient, random distribution is possible, but still sometimes can happen. So on average, I can say my chain length will be not very big. On general, it is supposed to be alpha. And because alpha is less than 1, so ideally it will be 0 or sometimes 1, mostly 1. And alpha is less than 1. But few cases only, it could be bigger than this. But because it's a simple uniform hashing, so SUS ensures that chain doesn't increase too much. On the other hand, if I have alpha to be greater than 1, that will be the case when n is less than m. That obviously means I am going to have multiple nodes or multiple values, elements in the chain. It is obvious because my total length is already going to be, or slots are lesser, values are more. So multiple elements in the chain. In that case, on average, what will be the search time? So average case or even worst case, searching will depend on the length of the chain. That is obvious. Worst case will mean full length will be traversed. Average length means half or expected value will be traversed. Insertion, obviously, order of 1 is guaranteedly possible. Deletion, again, in worst case, it will be length, full length. And average case, again, length dependent. So in worst case, the length will be full explored, and average case will also mean length dependent. So if I have SUH, my chain length on average is going to be alpha. So if I have an unsuccessful search, things are simple. How much time I am going to take? Unsuccessful case on average, or I'll say even if I say worst case will mean full length will be traversed, guaranteedly theta of alpha. Because full length of the chain will be traversed and chain length I have assumed to be alpha, and SUH will ensure alpha plus minus something, but more or less averaged alpha length will be assumed, or it will be guaranteed through SUH. So worst case performance is going to be theta of alpha, but this is not sufficient to write because alpha can be less than 1 also in some cases. If alpha is less than 1, this notation will be incorrect. So I will say the unsuccessful case on general, we will say theta of 1 plus alpha, because one time will be hash computation. That calculation has to be done. Minimum one order of 1 time is guaranteed for hash computation, and alpha is your searching time, unsuccessful search in the chain. So I can say this time is going to be theta of 1 plus alpha in worst case. And worst case will mean, or effectively, I will say unsuccessful guaranteedly means worst case. So unsuccessful obviously means full X length has to be explored. What about successful case? So successful case now, best case, order of 1, obviously. Worst case, again, I have to explore the full length. That will obviously mean theta of 1 plus alpha, because alpha times I have to go through that pull, and 1 is time for the hash function. If alpha is less than 1, then 1 plus alpha will mean 1 effectively. If alpha is very big, let's say alpha is 10,000, this one will be ignorable, but we don't know, so we write 1 plus alpha. Average case. Average case, you could say order of 1 plus alpha, not more than that, but probably I can say I need to calculate average case with more carefully using expected values. So in mathematics, you have studied expected value based calculations, knowing that, say, length of each chain is Li for I equal to 0 to m minus 1, and then calculating the expected value of Li and then doing this calculation. This is again shown in the book. This comes out to be theta of 1 plus alpha. And you have given in the book theorem 11.2 to prove this. So you must read that proof and understand that. This proof for the unsuccessful case is also given as a theorem 11.1 in the book. So you should also read this. But loosely speaking, I can say this is easily understandable, that loosely for average case, I can say average case means half length to be searched, half of the chain to be searched on average. Half of the chain means alpha by 2. So effectively, the total time taken will be approximately theta of 1 plus alpha by 2. In terms of a notation, this is normally notated as theta of 1 plus alpha, and 1 being needed because alpha could be in any range. So this way, it will be effectively there. But effectively now, you can easily see hash function can directly be used, and you apply h of k. This becomes directly the index number into your storage table, and you can use the storage table. So it is effectively generalization of array usage. And hence we always say through hashing, you can achieve a lot of functionality over keys which are range of 0 to n minus 1, and still hash function can be used. For example, in STL, you use various concepts like hash or map or unordered map. All these things effectively are closely related to the concept which we have discussed. And there also collisions are internally handled. So collisions are also being resolved, and there are algorithms to do that. In cryptography also, in storage of the safe security also, lot of hashing functions are used to ensure some storage, and then obviously hashing has a lot of applications. So in networks, in security, in STL, and anywhere else, you will study cryptography and the hashing in a more detail. I'll stop here, and probably now you can explore this with more detail.